In the previous section, we described basic optimizations you should implement as basic programming practices for all FPGA VIs. By the end of this module, you will be able to define FPGA IO terminology. Okay, so now we're going to go to Lesson 4, which is using FPGA IO. So as a quick overview, we're going to give you an introduction to it. We're going to talk about configuring FPGA IO. We'll talk about different IO types. We'll talk about using integer math, using CompactRIO IO, and how to handle FPGA IO errors. So on this slide on the top right, you see an example of an FPGA IO item. So FPGA IO items, they connect the IO to the FPGA logic. So this is the way that you'll get signals into and out of the FPGA. Each FPGA IO item has a type like analog or digital. So you might have an analog input that's coming into the FPGA, or you might have like a digital output that the FPGA is sending out. FPGA VIs can have multiple types of IO items. So they can have analog inputs, outputs, digital IO. There might be several digital IO lines on a particular FPGA VI. If you go to the NI example finder, you can navigate to Toolkits and Modules, FPGA, CompactRIO, Basic IO, if you want to take a look at some examples of different IO that you're using on a FPGA. So let's talk a little bit about FPGA IO terminology. So first, let's talk about a terminal. The terminal is the actual hardware connection. For example, on a CompactRIO module, you might have an actual pin for a digital IO line. Next, we have an IO resource. So the IO resource is a logical representation in LabVIEW FPGA of that hardware terminal. So for example, in that previous slide, you saw an IO node, which is representing that particular, possibly a digital IO line that's on your FPGA. And then lastly, you have an IO name. So in the LabVIEW project, you can assign that IO resource a name. So instead of just having it look like digital IO line 0, it could be something like emergency stop line. And you can give it something that makes a little bit more sense and it makes your code a little bit more readable. Now you can define FPGA IO terminology. Next, we will add FPGA IO to a LabVIEW project and access FPGA IO in an FPGA VI. In the previous section, we defined FPGA IO terminology. By the end of this module, you will be able to add FPGA IO to a LabVIEW project and access FPGA IO in an FPGA VI. Okay, so let's talk about configuring FPGA IO. So the way that you would add FPGA IO to your LabVIEW project could differ depending on what kind of target you're using. So if you're using CompactRIO, what you can do is you can detect the modules when you add your chassis, and this is an easy method because all the FPGA IO will be added automatically. If you're using R-Series, what you can do is you can manually add FPGA IO. When you're using R-Series, there's going to be a lot of lines typically. So by manually adding the FPGA IO, you can select which exact FPGA IO channels you're going to be using in your project. So when you're adding a CompactRIO to your LabVIEW project and it's already on the network, what you can do is when you're adding it, it'll ask you, do you want to discover C-series modules? If you click discover, then what will happen is it'll go to the LabVIEW project will go to the CompactRIO, find out what modules on there, and it will automatically add the FPGA IO for those modules to your project. In this slide, we see how to add FPGA IO to a R-Series project. So if we look over there on the left, we've got a project with the R-Series FPGA target. And to add IO, you would just right-click that FPGA target, go to New, and select FPGA IO. And that'll launch the window that you see on your right. So you can go through the different connectors and add specific lines that you're going to be using. And that's the way that you would add specific FPGA IO to a R-Series project. And we'll see this later in a demo. So in this slide, we see the FPGA IO palette. And this is where you would get functions and nodes that relate to IO. So for example, you can place down an IO node, and that's the way that you would access the values of IO. There's IO constants, methods, and properties, and we'll talk about those a little bit later. So here we see two methods of getting that IO node on your block diagram. One way is you can place down an IO node from the functions palette, and then you can right-click it, go to select FPGA IO, go to Module 1, and then select the particular Module 1 TC0 IO from your project. The other way you can do it is you can go straight to your Project Explorer and then find your IO. So in this case, we found and browsed to Mod 1 TC0, And what you can do is you can simply click and drag that onto your block diagram, and it'll be placed down there for you. So this is probably the easiest method to do it. Now let's go and take a look at this in a demo. Okay, so the first thing I'm going to demo is adding I/O to an R-series board. So we can see in our project that we have a R-series board right here, a 7852R. And what we're going to do is add some I/O to it. So right now, we don't have any I/O listed in our project, but we can right-click and go to New, and we can go to FPGA IO to add our I/O. So I'm going to select this. It's going to pop up this window, and I can kind of navigate through the I/O that's available on my R-series board. So I'm going to say, let's say in this project I happen to be using AI0, and I also need to use digital IO 0 as well. So now I've added these. I'm going to click OK. I notice that on my project, I've added AI0 and DIO0 on connector 0. Okay. So one thing that might be useful is AI0 is not super descriptive, so maybe I want to give it a more descriptive name. So I can right-click here or press F2 to rename. And instead of calling it AI0, I'm going to call this accelerometer 0. And then here, for digital IO 0, I'm going to call this emergency stop. Okay. So now I've got a descriptive name for my I/O, and I'm going to go to a VI, go to the block diagram, and I'm going to add my I/O. So I'm going to show you two ways of doing it. One way, which is probably the easiest way, is you can just drag it straight from your project into your block diagram, and now I've got my I/O here. The other way of doing it is you can right-click, go to FPGA IO, put down an I/O node, and notice that it doesn't know which specific I/O it's associated with, and you can left-click it, and then browse to whichever one you want to use. So in this case, I'm going to choose emergency stop, and now I've got an I/O node where I can access the value of emergency stop. Okay. So let me just close this. And now I'm going to bring up a CompactRIO project. So now here I've got my CompactRIO project, and what I've done is I've added the CompactRIO, and I've automatically discovered its different modules. So notice that I've got module 1 here with this I/O. I've got module 2 with some more I/O, and I also got module 3 with some more I/O. In this case, this one's analog output 0. So let me go ahead and open this up. So let's say analog output 0, and I can rename that, maybe call this motor or something like that. So now I can just drag this from here, from my project, into my block diagram, and I can start using it. Okay, and that's pretty much it for adding I/O for CompactRIO projects and also R-series projects. Now you can add FPGA IO to a LabVIEW project and access FPGA IO in an FPGA VI. Next, we will describe different FPGA IO data types. In the previous section, we added FPGA IO to a LabVIEW project and accessed FPGA IO in an FPGA VI. By the end of this module, you will be able to describe different FPGA IO data types. So in this slide, we have an overview of different I/O types that are available to you on FPGA. So here, we've got a digital line, and that's going to write and or read a Boolean value to and from a digital line. So it's going to be one line, and you're going to be able to send it a true or false to either set that line or read the value of that line. We also have a digital port. A digital port is a collection of digital lines. So if we take a look at that screenshot there, we have a DIO port control, which is a 8-bit unsigned number going into the DIO port 0 there on the IO node. That 8-bit unsigned integer is actually representing 8 separate digital lines. We also have analog IO. So this is going to allow you to read or write data from an analog channel. So in our series, analog IO is going to be represented by integer values, and we'll talk about this more later. And CompactRIO will generally represent that using fixed point data types. There are also other IO types for other specific modules. So there are motion CompactRIO modules out there, and those will have their separate I/O type and also CAN modules as well. So let's talk about digital I/O. So if you're wanting to set or read individual lines, then that's going to be using a Boolean data type. So each line can either go high or low, and that's going to be represented by a true or false Boolean value. A port is going to be a collection of lines. So it could be a collection of 8 lines or 16 lines. So with a port, you're going to indicate that with an integer data type. So if you're trying to do a port of 8 lines, for example, you would need to represent that with an 8-bit integer. Depending on your hardware, digital I/O can be either unidirectional or bidirectional. So for example, you might have a digital line with a particular module that only does digital output, or another one might only do digital input. Some hardware can do digital I/O on each line, so each line can either do input or output. So if your digital I/O line or port is bidirectional, and you want to change the direction of the line or the port from the FPGA VI, there's a method for that, and you would just select the set output enable method and determine it that way. So later on this lesson, we'll talk a little bit more about I/O method nodes. So here we have a slide talking about creating counters from digital I/O. So an FPGA does not have built-in counter hardware, so there's not going to be a counter line. So if you want to implement a counter, you would have to program that in FPGA. The minimum input pulse width detectable is going to depend on the loop period and also your hardware. As fast as that loop is running, that's how fast it's going to be able to detect a minimum input pulse. On some hardware, you can get improved performance by replacing the while loop with a time loop. So a time loop is going to be something called a single cycle time loop, and we'll talk about that in a later lesson. So let's take a look at this block diagram here. So what we see here is an implementation in FPGA for a counter, in particular a 16-bit rising edge counter. So let's focus on that top part for now. So on the top part, we're reading from the DIO0 line, and essentially what we're looking for is take a look at that greater than function. We're looking for a point where the top input is going to be true and the bottom input is going to be false. And that's going to represent a rising edge. So if you think about it, a rising edge is when that digital line goes from a false value to a true value, which is the same thing as it going from a low voltage to a high voltage. So every time that greater than function detects a rising edge, it's going to go down to the bottom section of this code and it's going to increment the count. So essentially you'll see that in that U16 integer, we're keeping track of a 16-bit count. Notice also that the loop condition terminal has an input of false, so this loop is just going to run forever. Also, if you look on the left side, there is a Boolean for resetting, so if that Boolean goes true, then it's going to reset the count back to 0. Let's talk about analog I/O. So different devices are going to have different default data types for analog I/O. So for example, if you're using an R-series device, the default data type is going to be a signed integer. So you're going to have a 16-bit or 32-bit signed integer depending on which device you're using. So for R-series, that data is going to be raw. It's going to be calibrated, but it's going to be unscaled. So that 16-bit or 32-bit number, if you want to convert that into engineering units, you're going to have to go from that number into a voltage, so you'll have to do some scaling. And we'll talk about that more later. If you're using a CompactRIO module and you're doing analog I/O, generally you're going to get your data returned as fixed point data, and this data is going to be calibrated already. So we'll talk about fixed point a little bit later in some of the later lessons. If you need to do floating point operations or analysis, you can either do this on the FPGA or you can also do it on the host. Now you can describe different FPGA I/O data types. Next, we will scale R-series analog I/O by using integer math. In the previous section, we described different FPGA I/O data types. By the end of this module, you will be able to scale R-series analog I/O by using integer math. Okay, let's talk about using integer math with analog input and analog output. So with R-series cards, a lot of times what will happen with analog input is it'll convert a binary representation of the voltage to a signed integer. So for example, the analog input would be reading a voltage. Maybe it's going from -10 volts to 10 volts. And then in the FPGA, it makes it into a binary representation of that. And if the FPGA hardware for that is analog input with a 16-bit resolution, then it's going to use 2 to the 16 bits to represent that voltage. So at that point, you have a binary number that has 16 bits of representation that is representing that voltage. What you can do to get that back into engineering units, one way you can do this is you can pass this raw unscaled binary data to the host VI for conversion to volts or other units. On the opposite end, with analog output, you could start in the host VI, and then you can take an engineering unit of volts and then change it into a 16-bit binary representation. And then you can write that binary representation of the voltage to the D to A converter of the analog output. So let's take a look at the numeric palette. So a lot of the basic numeric functions on the FPGA target are still available to you. So you have addition, subtraction, and things like that. Let's talk about integer division. So if you're taking a divide function and you have two integers going into that divide function, then it's not going to return an integer value. It's actually going to return a double precision floating point value, which is not supported on FPGA. So you must use other functions for integer math. So one way you can do it is you can use the scale by power of 2, which we've talked about before, if you're dividing by a number that's a power of 2, like 4. Or you can also use the quotient and remainder function. And that one is going to do the job, but it's going to take a lot more FPGA resources. So in this slide, we have an example of doing some scaling with R series in LabVIEW FPGA. So let's say we have an output coming out of that I/O node. So we're reading an analog input channel 0. And really what we want to do is we want to scale that by a factor of 0.7. So one thing we can do is we can try to get something close to multiplying it by 0.7 by multiplying it using integer values. So we can use a scaling factor here of 11500, and we can divide it by 2 to the 14th. And if you do that math, then what you actually get is 0.7019, which is a value that's very close to 0.7. So you can see in this example, we were able to multiply the value of analog input channel 0 by 0.7 using integers. So we were able to multiply by an integer and do a bit shift kind of function with the multiply by a power of 2 function to get something close to 0.7. So as I stated earlier, the R series FPGA IO node with analog values, it's going to return a binary representation of the voltage input. So for example, over here, we've got something with a 16-bit resolution on our analog input channel. So if you look at the bottom, we've got 0 going all the way to 65,536. These values are representing a voltage, but we're seeing the full resolution there. So if we wanted to convert this number, so if we want to convert 0 to 65,000 into something like engineering units, for example, negative 10 volts to 10 volts, then we would need to do some sort of conversion. So you can either do this conversion on the FPGA VI, or you could also send it to the host and have the host handle converting that binary representation into an engineering value. So conversion to binary representation is hardware dependent. Each hardware target's going to have its own specific voltage range. It's also going to have analog to digital conversion precision. There's going to be offset and auto zero values as well. By looking at the help documentation for the device you're using, you can use these hardware specific values and use the values for conversion of the binary data on the host. So at this point, it would be good to do exercise 4.1. In exercise 4.1, we're going to take a look at R series IO. So what you'll do is you'll create a project, have an R series FPGA target there, and you're going to add IO to it. Then you're going to create a VI that uses that IO, and then you're going to simulate the execution by executing the VI on a development computer. And then when you run it, you're going to get simulated values of that IO. So you're going to see simulated digital data and also simulated analog data. Now you can scale R series analog IO by using integer math. Next, we will describe the data type, module properties, and module methods associated with CompactRIO IO. In the previous section, we scaled R series analog IO by using integer math. By the end of this module, you will be able to describe the data type, module properties, and module methods associated with CompactRIO IO. Okay, so let's take a look at using CompactRIO IO. So when you're using analog input and analog output modules with CRIO, they're going to typically use a fixed point data type. So fixed point data type, we're not going to go into the specifics here, but we will talk about it later in lesson 7, signal processing. But for now, just know that fixed point data type, it provides some of the flexibility of floating point data type, but it also maintains the size and speed advantages of integer arithmetic. So it's going to kind of let you be able to do something close to floating point in terms of functionality, but it's going to be more efficient the way that it's implemented on the FPGA. So different CompactRIO modules can have different fixed point configurations. So the output or inputs of these modules are going to be a fixed point data type. Each one, depending on the module, the fixed point configuration might be different. Also, the methods associated with these modules will be different, and also the properties as well. So we'll take a look at a couple of these examples in the next slides. If you want more specific information on a particular module, you can go to the link in the help that's shown on this slide. So notice here on this slide that we've got a couple of different modules here. They're all analog modules, but they return fixed point data with different configurations. Okay, so the way that the configuration is going to be is it's going to be based on the accuracy and range of a particular module. Some I/O nodes will return scaled and calibrated fixed point values. So depending on the module, the I/O node might have, scaled values that are already in engineering units, and some might not. So let's take a look at an example here. If we look at the bottom, we've got a module there. It looks like it's an analog output module. And to the right, you see its fixed point configuration. We see things like the maximum that it can output, the minimum value, and also the delta. And again, we'll go more into this in the signal processing lesson. So in the middle one there, we have an analog input module. At the bottom, we have a thermocouple module. So we see that the fixed point configuration, the max and mins and deltas, are a little bit different for each of these. So this is just trying to highlight that depending on the module, the fixed point configuration will be specific to a module. Here on this slide, we see different module properties and methods. So each module is going to have its own specific properties that are associated with it, and same with the methods. So if you think about properties, properties are more like attributes of the module, and methods are more like actions that you can execute that are associated with the module. So if we look at the left here, we see at the top left, we have a 9263 module, which is an analog output module. So for that particular module, the only property we have available is module ID, serial number, and vendor ID. If we look at the top right, for that same analog output module, we have a couple different methods available. So we have a method that will do update, wait for update, and also write data. So those are all methods that are associated with that analog output module. If we look at the bottom left, we have an example of a property of an analog input module. So the NI9233 is the analog input module. Notice that one property that it has is data rate. It also has module ID, serial number, and vendor ID. For that same 9233 module, if you look on the right, there are no methods that are associated with that module. So at this point, if you have the hardware available to do this exercise, this would be a good time to do exercise 4.2, where we work with CompactRIO IO. So in this particular exercise, we're going to acquire 2 thermocoupled, and we're going to get that data, and we're going to take a look at it in the FPGA VI and subtract those just to see what the difference between the temperature is. So right now, what we're going to do is I'm going to do a quick demo of the solution, just so you can kind of see what's going on here. Okay, what we have here now is exercise 4.2, and we've got our project right here. And we've got our CompactRIO and our FPGA target. So what you would have done in this exercise is you would have built this particular VI. So if we look at this VI over here, the front panel, we've got thermocouple 0 and thermocouple 1, and the difference between the two. So these are all indicators. If we look at the block diagram, what you would have done is you would have taken the thermocouple IO. So if we go back to our project and go to module 1, notice that we renamed thermocouple channel 0 as thermocouple 0 and TC1 as thermocouple 1. So they show up with more readable names. And we put this down in a FPGA IO node, and we've also expanded it so we're reading 2 different values from this same node. Okay, so we're outputting the value of thermocouple 0 here in this indicator, and thermocouple 1 is being output on this indicator, and we're also doing a subtract right here. So we're subtracting those 2 values and getting a thermocouple difference. Notice that the font here, the color of the font, the color of the wires, and the color of the indicators are all gray. And that gray color indicates that is a fixed point data type. So notice that it says FXP. That shows that it's a fixed point data type. And again, we'll talk about that more in Lesson 7, signal processing. So let's take a look at the values up here. So let me go ahead and stop this. In this case, when we created this VI, we would have run it and compiled it. In this demo, we've already finished the compilation and it's already running. Let me hit stop. So if we look at these values, notice that these are probably not Celsius or Fahrenheit values. So in the case of this particular module, the values that it returns, they are calibrated. However, they have not been scaled for Fahrenheit or Celsius. So to do this, we could either do those calculations on the FPGA, or we could send it up to the host, which can handle floating point operations with ease. Another thing I would want to point out is how fast is this while loop running? If we take a look at it, it's trying to run as fast as possible. We haven't added any timing to it, so we haven't specified a loop rate or anything. We'll talk about that more in the next lesson. Now you can describe the data type, module properties, and module methods associated with CompactRIO IO. Next, we will handle FPGA IO errors. Previous section, we described the data type, module properties, and module methods associated with CompactRIO IO. By the end of this module, you will be able to handle FPGA IO errors. Okay, let's talk about handling FPGA IO errors. So by default, you might have noticed that the IO nodes do not have any error terminals. However, if you do want to look at the errors for a particular IO node, what you can do is you can right-click that IO node and select Show Error Terminals. And once you've done that, it'll look like the screenshot that you see to your right. So in that screenshot, notice that the error terminals do appear, and you can extract that error information and send it to error handling code. So error information is useful for debugging and validating data, and it's essential in some cases, for example, if you're working with some safety equipment and things like that, but it uses space on the FPGA and can slow execution. So every time you're outputting the errors, it takes some FPGA resources to actually implement that. So in general, you only want to show the error terminals if you really need to use something with those errors. If you're not using the error information, you just typically want to not show those error terminals. Okay, so now let's talk about error cluster optimization. So just some things to keep in mind when you're dealing with errors on FPGA. So when FPGA resources are limited, these are some things you can do instead. So if you're only showing that error terminal, and the only reason you're using the error wire is for sequencing and for determining the order of execution, then you shouldn't be using error terminals for that. Instead, you should use a sequence structure for data flow instead. If you're using a sequence structure for data flow, you're not going to have to use extra FPGA resources to communicate that error information along that error wire. So don't use error wires only for sequencing. Instead, you can use a sequence structure for that. Again, only show error terminals for modules whose functions are critical to that system operations. So, for example, only show that error terminal if you're actually going to need to use that information about the error in your program. Also, if you have a I/O module in multiple places and you only want to check on some of the general errors that are associated with that particular I/O module, then show the terminals only once for that module, and then you can kind of periodically check the errors on that module instead of showing the error terminals on every instance of that particular I/O module. And that's one way to save space and not have to use so much space for every single time you're showing that error wire. Sometimes when you're programming LabVIEW for Windows, you use the error clusters and you kind of pass them through your entire program and then show the error at the end. In FPGA, you don't want to do that. It's going to take up extra resources on the FPGA that you don't necessarily need to use. So instead of passing the error cluster all the way through your program, one way you can save space is you can handle the error right where it occurs. So, for example, if you have an I/O node where you're monitoring the errors for it, you can unbundle the error wire right there and then take a look at those items and handle that error immediately instead of having to pass that error all the way through your program. That way you fix the error immediately and you don't have to use extra resources passing that error all across your program. So this slide talks about error clusters for reliability. So some examples of FPGA IO errors that need to be handled are things that are associated with safety critical operations. So for example, if you've got some I/O and it's controlling a large motor or something like that, that might endanger people's lives, then you might want to check that I/O and make sure that that I/O is working properly. Other ones are there's module-specific error codes for specific CompactRIO modules. So sometimes you'll need to use that error for a particular instance. So for example, if you're using the NI9802, which is a removable storage module, there's a particular error code that's associated with file not found. So if you need to check that for that particular error, you'll need to use the error wire for that. Also, if you're using CAN modules, there are specific error codes that are associated with timeouts. So you might need to use the error wire for that as well. Another thing that you can use errors for is if a module has been removed from your CRIO, it's also going to output an error associated with that. So you can use the error to check whether your module is actually in its slot and operating correctly. Now you can handle FPGA IO errors. Next, we will implement loop execution rate using the timing express VIs.